So we do have Fourier series coefficients for periodic signals. What can we do for such periodic signals if we want to represent them in terms of their Fourier transforms? Do you remember what we were doing in continuous time for periodic signals, I mean? If you have a periodic signal, how did we find the Fourier transform of that? We found the Fourier series coefficients and inserted impulses at those at the corresponding harmonic positions. That's how we do it. We will do exactly the same. This is only for periodic signals, and from here we will find the Fourier series coefficients, and then we will make impulses out of them. That's the same strategy, both for continuous time and for discrete time. So what was the situation in periodic signals? A periodic signal could be represented as a summation of within a summation of a period, capital N. Capital N is the period of this signal. The Fourier series coefficient ak times e to the jk omega 0. Omega 0 was 2 pi over capital N, the frequency, times n. So here, these were the Fourier series coefficients. With those Fourier series coefficients, what we're going to do is we will represent our Fourier transform. Remember how we were representing the Fourier transform of discrete time signals. The Fourier transform was not capital X of j omega, it was capital X of e to the j omega. That's just the notation. And that is equal to summation for k. I will indicate the summation index later. 2 pi times ak times the impulse, delta omega minus 2 pi k over n. So it's the same. We are just inserting an impulse at the position of this ak with the value ak times 2 pi. That times 2 pi thing was also existing in continuous time, you may remember. If the Fourier transform, the Fourier series coefficients were ak's for a continuous time periodic signal, we were inserting an impulse with this magnitude times 2 pi. It's the same thing here. This summation is simply indicating that we are inserting all of these Fourier series coefficients. That's what it means. And it is indeed from minus infinity to infinity. You may be asking this question, if we have a finite number of AKs, then why is this summation infinity? Because we don't have a finite set of AK indices. They are repeating themselves. Capital N of them are distinct, and then they are repeating themselves. So this is quite simply the Fourier transform of our interest. So what does the overall layout look like? For example, if this is the frequency axis, it looks like this. You have at the frequency of 0 an impulse with the value 2 pi times a0, and then at the position of the frequency, and how are we going to find that frequency? We will think about that. 2 pi times a1. Now this frequency is the first harmonics frequency. And what is that? That is omega 0. Let's say. And that omega 0 is 2 pi over capital N. The first harmonics frequency. Then we have 2 pi times a2. And this is 2 omega 0. And it goes on like this. Then we have, for example, 2 pi times a capital N minus 1, which is the last distinct Fourier series coefficient. This frequency, let's not indicate as it is, but instead let's use a different color to start with the new set of impulses. This green thing is 2 pi times an, and that is simply equal to 2 pi times a0 because an is equal to a0. And the position of that is at 2 pi. Why is it 2 pi? Because it corresponds to capital N times omega 0, and capital N times omega 0 is capital N times 2 pi over capital N, which is 2 pi. So at 2 pi, it starting from 2 pi, it starts repeating itself. I should have a different color, but I don't have it now. So I will try to indicate it like this. Here there's an impulse at minus omega 0, and the value is 2 pi a minus 1. But this 2 pi a minus 1 is the same as 2 pi a n minus 1. These two are the same. So everything is periodic because the discrete time Fourier transform is 2 pi periodic. You have a region like this from here to here, and that region is repeating itself towards right, and it's also repeating itself towards left, like this. And you have to equally space impulses. How many impulses will you insert within here? You will insert capital N impulses, equally spaced. And that equal spacing is 2 pi over capital N, which is omega 0, 2 omega 0, 3 omega 0, etc. So this is how you render and plot the Fourier transform of discrete time periodic signals. Of course, if it's not periodic, then we don't talk about the Fourier series coefficients. We don't have any such expression. And over there, you have to just find the Fourier transform, discrete time Fourier transform formula, using the formula or using the properties that we will see. You just have to do it that way. Let's see two examples, a couple of examples. The first example is the famous cosine, the trivial example, cosine omega 0 n, and omega 0 is 2 pi over capital N, whatever that capital N may be. And here you don't even need to evaluate the Fourier series coefficient since it's a cosine using the Euler's formula. It is 1 over 2 e to the j omega 0 n plus 1 over 2 e to the minus j omega 0 n. So it has two Fourier series coefficients. One of them is 1 over 2 and the other one is also 1 over 2. They are a1 and a minus 1. And how can we express the Fourier transform then? Using two impulses. Those two impulses are, how do they look like? They are delta. By the way, there is a 2 pi times 1 over 2. 1 over 2 is, let's call it a minus 1 or a1, whichever you may choose. They are the same. Times delta. Let's think of the impulse corresponding to omega 0. Where is that impulse? It is at omega 0. And we have to indicate it like this, delta omega minus omega 0. That is an impulse at omega 0. But it's only one impulse. Suppose this is the center. We are trying to represent this x of e to the j omega. This is at omega 0. And let's assume that 2 pi over capital N is like, for capital N we have a value of 5, let's assume. So it's 2 pi over capital 5. It's not a capital 5, sorry about that. It's just number 5. So it's an example I'm telling you. With that example, we have 2 omega 0, 3 omega 0, 4 omega 0. And then 5 omega 0 corresponds to 2 pi, doesn't it? It corresponds to that. And we have a minus omega 0 with the same impulse. By the way, the height of these impulses are pi and pi, because 2 pi times 1 over 2 is pi. But these two impulses are in the center, and they must repeat themselves around 2 pi, around 4 pi, around 6 pi, and around minus 2 pi, minus 4 pi, minus 6 pi as well. So we have to make an extension of this thing. This is the impulse that I have drawn, pi times delta omega minus omega 0. I have to put the same impulse here as well. I have to replicate it here. Then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 4 pi, and here we have to repeat that impulse. I'm repeating this impulse like this, towards the right and towards the left as well. How can I repeat that? How can I indicate the repetition of these impulses? By making it a summation. Let's assume that the summation is over L. It's an infinite summation towards right and towards left. And we have pi times delta omega minus omega 0 minus 2 pi L. This is the thing that you have to write. And in fact, within this summation, we have to put the repetitions of these impulses as well. This impulse must repeat itself here, and it must also repeat itself here, etc. So it is also 2 pi periodic, and that is plus pi times delta. The first one is at minus omega 0, so it is delta omega plus omega 0 minus 2 pi L inside the same summation term. So can you now see the difference between two alternative representations of the same thing? Usually when I ask a question like this in the exam, let me tell you how the student answers this question. So this is student says that the Fourier transform corresponding to that is pi times delta omega minus omega 0 plus pi times delta omega plus omega 0. This is the answer of the student. This is the answer of a good student, by the way. Okay, for the person who is able to solve a bit of this thing. But the correct answer that I expect for such things is not consisting of only two Fourier series coefficients. These two Fourier series coefficients are the distinct coefficients. They must repeat themselves 2 pi periodically. So the correct answer is, as here, L from minus infinity to infinity in a parentheses pi delta omega minus omega 0 minus 2 pi L plus pi delta omega plus omega 0 minus 2 pi L. And this is the correct answer that I expect. Okay, you see the difference between them. This one is just periodically replicated by 2 pi. The periodically replicated version of the top. And that is the correct answer that you should be able to give, or I'm expecting. Okay, another example. Let's see another example of this Fourier series coefficient thing. You see, whenever something is periodic, that period is a very certain frequency. It corresponds to a very certain frequency. For example, it is periodic with capital N. Therefore, there exists a certain frequency of 2 pi over capital N, that is omega 0. And there are harmonics of those things like 2 omega 0, twice of that, 3 times of that, etc. So that those things plus their integer multiples are very pronounced, very strongly existing harmonics. Those strongly existing harmonics are represented as impulses on the Fourier axis. So the Fourier transform deliberately indicates a very strong component at omega 0, for example, or at 2 omega 0, 3 omega 0, whatever. That's why there are impulses in the Fourier transform for periodic signals. However, if the signal is not periodic, then the existence of a certain harmonic is out of question. There is no such thing. Then the Fourier transform is a curve. Okay? There is no impulses over there. The impulses only appear for periodic signals. Another example, another famous periodic signal is a periodic impulse train from minus infinity to infinity, delta n minus k times capital N. So this is a discrete periodic signal with period capital N. And in between they are all zeros. This is your signal over the axis of N. A discrete time periodic signal of consisting of impulses appearing at periods of capital N. Now, what is the Fourier transform expression corresponding to that? For that, of course, since it is periodic, you have to find the Fourier series coefficients, and the Fourier series coefficients from the formula you may remember within a period xn e to the minus jk 2 pi over capital N n. This was the expression to determine the Fourier series coefficient, and it is within a period. Let's take the period from here to here, and within this period, one period, there is only one non-zero sample value where the value is 1 over there, and that is when n is equal to 0. When n is equal to 0, it is 1. For all other n values, it is zeros. When n is equal to, this becomes 1. And when n is equal to 0, this becomes 1 again. For all other n's, this becomes 0. So whatever the value of this, it is multiplied by 0. So this summation has only one coefficient, which is 1. And therefore, the outcome of this summation is 1 times 1 over n. So it is 1 over n, simply. This is the Fourier series coefficient. For which value of k? What is the k index that corresponds to this? For all values. For all k, it is identical to 1 over n. Then, what can we say about the Fourier transform? It's equal to 1 over n times 2 pi, that is 2 pi over capital N, times, for example, if it is A0, that we're talking about, then we have delta omega, because omega minus omega 0, omega 0, the frequency corresponding to A0 is not omega 0, 0 times omega 0, which is in the center. So we have an impulse in the center when k is equal to 1. It's again 2 pi over capital N times delta. When k is equal to 1, where is the frequency of that? It is at omega 0, or 2 pi over capital N, whatever. That is omega 0 anyway. Then for k is equal to 2, it's again 2 pi over capital N times delta omega minus twice 2 pi over capital N, or 2 omega 0. Plus, etc. For all of them, it's the same. So what you really need to do is you need to express this result as 2 pi over capital N summation. The index of the summation, let's give or say it as k, from minus infinity to infinity, delta omega minus k times 2 pi over capital N. And that is automatically 2 pi periodic. There is only one impulse in each 2 pi period. And if you want to visualize what's happening here, it is an impulse at 0 with the value 2 pi over capital N. And then at 2 pi over capital N, let's call it here 2 pi over capital N, which is omega 0, by the way. It's the same impulse value. At twice of it, we have another impulse, etc. And finally, at n times 2 pi over capital N, which is 2 pi, we are meeting the same impulse, and the impulses just continue. So these impulses are periodic with a period. What is the period? What's the width between two impulses? It is 2 pi over capital N. It's periodic with this. And capital N is an integer. So it is automatically periodic with 2 pi as well. Because if it is, let's say, periodic with period 2 pi over 5, then after 5 periods, you meet 2 pi. So it is also periodic with 2 pi. And that condition of being periodic with 2 pi is satisfied. Because, as I say, capital N is an integer. If it's a rational number, by the way, it is still valid that it becomes periodic with 2 pi. But if this capital N is an irrational number, then you cannot talk about a period with, of 2 pi. A period of 2 pi cannot be told. But we know that for a discrete time signal to be periodic, it must have a period of integer. So this capital N is definitely integer. These two examples of a cosine and the periodic impulse train are the two most typical Fourier series examples that we know. But there are other Fourier series examples as well from that chapter. Whatever Fourier series example you may think of or you may come up with, I can easily ask the same question like this: what is the Fourier transform? Because since you can find the Fourier series coefficients, just convert the Fourier series coefficients to impulses and call it as the Fourier transform. All right. Now, so much about periodic things. Let's continue with some normal Fourier transform examples of non-periodic or regular signals, like xn is equal to e to the absolute value of n. Let's not call it e, let's call it a to the absolute value of n. Let's start by writing the Fourier transform formula. What was the Fourier transform formula? It was x of e to the j omega is equal to an infinite summation from minus infinity to infinity. The signal times e to the minus j omega n. And that is equal to that n in the exponents can be expressed in common, but since it's a magnitude or absolute value of n, we have to think of and from minus infinity to minus 1 case, the negative case, separately. And over there, what is the magnitude or absolute value of n? It's equal to minus n, equal to minus j omega n, plus all the others from 0 to infinity. Over there, absolute value of n is the same as n. We have a to the n, e to the minus j omega n. So you must split the case into two and evaluate the two summations independently. The first summation is summation n from minus infinity to minus 1 a times e to the j omega to the power, or a inverse e to the minus j omega to the power n. Let me write it like this, plus from 0 to infinity a times e to the minus j omega to the power n. So they really look like this. This is, for example, f to the power n, an infinite series sum, f to the power n. This is another infinite series sum. Let's call it g to the power n or something like that. This one is, I guess, easier for you because we know that it is 1 over 1 minus g. This one, for this one, you must make a change of variables. Although I said that this is minus, let me put the minus here. You should call something like this. Change k is equal to minus n. If you make that kind of an exchange, then this thing will be k from 1 to infinity f to the power k, right? The order and the indexes will be negated. So that's it. What is the difference between these two summations? You have to be careful about only one single point. This one is from 1 to infinity, k from 1 to infinity, f to the k. This is n from 0 to infinity, g to the n. So one of them is from 0 to infinity, the other one is from 1 to infinity sort of thing, because a 0 is not common for both of them. There is only one difference like that. And that difference, this one, by the way, is easily 1 over, I'm writing this one, this summation first. That is 1 over 1 minus a e to the minus j omega. The other summation, the first summation over there, is like this, a e to the j omega over, because there is one term, 1 minus of that expression, you may say, 1 minus a e to the j omega. And you say that this is the Fourier transform. You may put the expression in a box and say that this is the total expression, and you get 10 points. But of course, since that's a very typical thing, I will continue with the simplification of this expression. It can be a little bit simplified. If you can call it a simplification, of course. 1 minus a square, or let's call it in a more compact form. 1 minus 2a cosine omega plus a square. As you see, it looks like something like 1 minus a square over 1 plus a square, and in between there is a cosine term in the denominator. This thing is a little bit more complicated than a to the absolute value of t in continuous time Fourier transform. But this result that you can see here, they are available in tables. For example, if you take a look at the Oppenheim's book, there are some typical transform pairs. Such typical transform pairs table also exists for continuous time Fourier transform as well. There's a table like that in Oppenheim's book as well. This one is in the table. The first order a to the minus n u of n sort of thing is also in the typical transform pairs table. Those tables will be available to you in the examination. Or let me put it like this. Please understand what I'm telling because that is critical, and that is very critical for the final examination as well. For the first exam, I gave you a table. Okay? That table will be available for the second midterm too. But you have to also bring the tables from the book by taking photocopies or by taking printouts if it's in the digital form. But the printouts that you will bring will be only for typical transform pairs and transform properties for continuous time and for discrete time. Transform properties, typical pairs. There may be other tables in the book as well. For example, there's a very small table showing the Fourier transform formula. Okay, the inverse Fourier transform and the forward Fourier transform. A small table. Do not bring that. The only tables that you're allowed will be typical transform pairs and properties. Yes. That is valid for Fourier series in continuous time and in discrete time, and Fourier transform in continuous time and discrete time. But your printouts or photocopies must contain only these and only from the Oppenheim's book, not from other textbooks or other resources. Only from Oppenheim's book. And there may be situations like this. Since the table contains some other text as well, when you take a copy of that page using the photocopy, those other places are also copied. Please cut them. I don't want them. Okay? A clean list of tables will be available to you, nothing else. That something else, if you bring, will be a headache for you, and your examination will be cancelled. Okay? Do not bring anything else. Do not write anything on those tables. Just clean tables from Oppenheim's book. Is that clear? In the exam. You have to bring yourself. That's why I'm telling you. So be careful about that. Do not try to bring anything else. Now, that was a huge parenthesis, but what is more important than that, using these typical transform pairs and using the properties, what were those properties in continuous time? For example, what happens when you shift? What happens when you convolve two signals? Convolution property, shifting property, time scaling properties, etc. There were several properties. Using the properties and using the transform pairs, typical pairs, you will combine and solve your questions. That's how you usually solve questions. So this is one of the signals that you may start with. If the question is a modified version of this, then you may start by using this as the answer immediately. You don't have to solve this to obtain it. Just start by using it. That's something that you can do. All right. Another example which also exists in typical transform pairs is a rectangular pulse x of n is equal to 1 for magnitude n is less than or equal to capital N and 0 else. So what is that? It's a rectangular pulse from minus capital N to capital N, all ones, and out of it, it is all zeros. Something like this. It's a rectangular pulse, in other words. This rectangular pulse, how many items are there in this rectangular pulse? 2n plus 1. There's also 1 in the 0, so that is a plus 1. What is the Fourier transform? The Fourier transform is an infinite summation of xn e to the minus j omega n. xn is valid only from minus n to plus n. So why not writing the summation from minus n to plus n only? Because out of these summation bounds, it is all zeros. And inside these summation bounds, it is 1 times e to the minus j omega n. So it is this summation, quite simply. And that summation has a simplification. If you don't know the simplification, normally in an exam question or something like that, you may just leave it like this. This summation will give you the Fourier transform, you can say, but there is a simplification, and that simplification is in the table given as sine omega n plus 1 over 2. As you see, it's a little bit complicated and difficult. Sine omega over 2. Okay, so this is a strange expression, and it comes from the simplification of the top summation term. And that strange simplified form, it's a bit difficult to see whether it is 2 pi periodic or not. For that, you may want to make substitutions and verify yourselves that this is indeed 2 pi periodic. But it also has a certain plot in the magnitude. Well, it is real anyway, so we don't need to plot the magnitude. By the way, can you guess why it became real? Why isn't this a complex number? Why did this become real? Because it's a Fourier transform, and Fourier transforms have complex exponential terms multiplied. So the Fourier transform could become complex easily. But this one became real, whereas a to the minus n un, the Fourier transform of that was not real. That was the first example we saw last hour yesterday. But this one is real, the Fourier transform. Why? No? Why is the Fourier transform of this real? Why is the Fourier transform of this real? Yes, they are even signals, or they are symmetric signals around the origin. This one is a symmetric signal, this one is a symmetric signal, and for symmetric and real signals we come up with real Fourier transforms. And not only that, they are symmetric Fourier transforms as well. So that real and symmetric Fourier transform for this rectangular box, what does it look like? I will just give you a rough idea about how it looks like. It looks like something like this. I'm very sorry about my poor drawing, but the situation is something like this. At pi, it is shrinking towards pi, and this is 0, and this is 2 pi. Since everything needs to be periodic, it looks like a sink, by the way. It is decaying like this, just like a sink, but up to pi only. A sink is not 2 pi periodic. It is like cutting the sink and making it periodic or something like that. It decreases and then increases to make another sink looking shape, and then decrease again. But around 4 pi, it has to increase again. Around 6 pi, it has to increase again. And everything must become 2 pi periodic again. It's a 2 pi periodic sink sort of thing. And this sink behavior is something expected because that's a rectangular box. Rectangle produces a sink shape. Okay, now the next example is another quite typical one. It is an impulse in the center, delta n. This delta n, the Fourier transform of delta n is what? When you take a look at the Fourier transform, the Fourier transform expression from that summation will give you only one non-zero in the summation, and that non-zero is at n is equal to 0. So the result is eventually 1. Okay, that summation will give you a 1. So this is the Fourier transform. But what does it mean? I mean, what kind of a Fourier transform is that? Is it 2 pi periodic? Certainly it is, because it's constant. It is 2 pi periodic as well as 1.5 periodic as well as everything, because it's constant. It's periodic just indefinitely. How can we relate this signal x of n is equal to delta n to this shape? Why am I trying to relate to this shape? Because this shape, if you may remember, was corresponding to a rectangular box like this, the Fourier transform of this, from minus n to n. What happens if minus n or n, this index, is just 0? Isn't this the narrowest rectangular box? When capital N is equal to 0, that's what it is. And this really corresponds to the rectangle when capital N is equal to 0. And when capital N is equal to 0, what was the Fourier transform shape that I was drawing here? What was the expression? It was sine omega n plus 1 over 2 over sine omega over 2, wasn't it? That was the expression. Now make this 0, so it becomes sine omega over 2 divided by sine omega over 2, and that is 1. You could also answer the same question by knowing this portion only, because this impulse is corresponding to the rectangle with n is equal to 0, and the Fourier transform of rectangle is this large expression. This is just a special case where capital N is equal to 0, and when you make capital N to be equal to 0, you get sine omega over 2. Sine omega 0 plus 1 over 2 is sine omega over 2 over sine omega over 2, which is 1. So that's the same answer. And the last example for today, and up to this point, you will be responsible in the examination. This is more like an example regarding Fourier series coefficients, by the way. When I give you the hint like this, I'm sure you will understand. E to the j omega 0 n is just a sinusoid, and this sinusoid, it's a complex sinusoid. This complex sinusoid has how many Fourier series coefficients? We will find the Fourier series coefficient and we will insert an impulse there. That's how we're going to solve it. How many Fourier series coefficients are there? 1. That is 1 times this, nothing else. So there is only A1 is equal to 1. And the frequency is at omega 0, whatever that omega 0 is. So where is the impulse? It is 2 pi times 1 times delta omega minus omega 0. For one impulse, do not forget to extend it to make it 2 pi periodic. Normally it was only at omega 0, now it is at omega minus omega 0 and 2 pi plus that one, 4 pi plus that one, or minus 2 pi plus that one, etc. So this is the thing that you have to always remember. The exercise that you must think of by yourselves is find the inverse Fourier transform of that. What was the inverse Fourier transform? X of n was supposed to be an integral of 2 pi from minus pi to pi, from 0 to 2 pi, wherever you may wish, of this expression. And whenever you restrict your integral within a 2 pi, it means that you don't have to deal with the 2 pi replicas. Only one set of those impulses is sufficient inside the integral, times e to the j omega n d omega. Now, is this equal to e to the j omega 0 n? Is it equal to e to the j omega 0 n? It certainly is. It is quite obvious. There is not even a necessity to show it. But you should be able to see it by yourselves. That's why I'm giving it as an exercise. We haven't seen much examples regarding the inverse Fourier transforms, unfortunately. But we know the formula for that. And we have, you will have the tables like that. From those tables, you should be able to find a few inverse Fourier transforms if you make an exercise with this one. Yeah. Yeah, there must be 1 over 2 pi. And that 1 over 2 pi will cancel this 2 pi delta impulse. Right? That's true. So, these are the things that you will be responsible with. Please come exercise. Do you have any questions regarding the examination? Typical. Yeah, tables will be, you have to bring the tables, clean tables, from the book of Oppenheim only. Yes. Yes, no, you will not bring the formulas of the transform and the inverse transform. Don't photocopy them. The only copies that you may bring will be properties and typical pairs only, not the definitions. I don't think so. You have to just learn it. Whenever you exercise more and more and more, you will just memorize it. You will know it. You have to know it.